Hello everybody, welcome to this Introduction to Geology course. My name is Paul Day, I'm a professor of geology, and I'll be the one that's leading this course. This is going to be the very first lecture in a series that I'm going to produce. The entire thing will be made available online, and if you're interested in learning about rocks, the earth, a little bit about the origins of the earth, how we do geological time, if you're interested in minerals, earthquakes, natural hazards, or the formation that you're seeing right in front of you, which is Morro Rock in Morro Bay, California, you're in the right place. This is the right class for you. So if you're interested in this, stay with me, go through the series. I would love to have you. Let's go ahead and jump into this Introduction to Geology. So the primary focus of this very first lecture is to understand the science of geology, which is to say, to understand how geologists think and reason, how they treat evidence, and how we examine that evidence. Through what lenses do we look at them? And so we're going to look at that. We're going to look at a little bit of the history of this because the way we've thought in the past certainly influences the way that we think today. Sometimes it's to reject it, sometimes it's to accept it, sometimes it's to use as a counterpoint. So we're going to be focusing on that quite a bit. So what is geology? What is it we're going to be talking about? Well, first off, geology is the science that pursues an understanding of planet Earth. It's usually subdivided into two subdisciplines, usually in the early going of somebody studying geology. An introductory student could either take a physical geology course or they could take a historical geology course. Physical geology examines materials composing Earth and seeks to understand the many processes that operate beneath and on the surface of our planet. That actually describes exactly what we are doing in this course. We will be doing a physical geology course. I'm intending to follow it up at some point in the future with a historical geology course, so I'll be looking out for that. Physical geology is the question of the materials. Here we see a mountain, right? We see these layers. They're twisted and turned and bent, and there's faulting actually happening in there if you have the eye to be able to discern it. What makes that happen? What's the process? How long does that take? What does that tell us about the Earth? What does that say about ourselves as residents of this planet? Historical geology. It seeks an understanding of the origin of Earth and its development through time. So historical geology is the story of Earth. When did it originate? How did it originate? At what point did it get oxygen in the atmosphere? How do we know this? How did the rocks play a role in life? How did the rocks play a role in our current existence? All of that is part of historical geology. And of course, the fossil record is a big deal. In fact, here we see a beautiful Tyrannosaurus rex skull that demonstrates that this is an animal that doesn't exist anymore. So this is something that came into existence in the past and went out of existence. It went extinct. So we're going to be digging into a little bit of the historical geology, but that's more of a focus that could happen in a future course. So if you're interested, please look out for that. So before we could dig into what it is that we think is going on today, we really need to look at the heritage of human thinking and what we've been working on. And of course, some of it is written down and some of it is not. But we do have very good records from great thinkers. I believe his name is Xenophanes, was looking at the question of how the Earth has changed and how it's evolved over time. And what does that evolution actually mean? So Xenophanes and later Herodotus, for example, observed fossil fishes and shells and concluded that the land where they were found had been underwater at some time. So here we find a fossil fish in China. China clearly is a landmass, yet there's fish in the rocks, fish fossils in the rocks. And so the conclusion was they had to be underwater. That is an evolution of the landscape. And so you can conclude that the Earth, as it looks today, didn't look the way that it looked back when that fish was living. Aristotle deduced that the Earth changes at a slow rate, and that these changes cannot be observed during one person's lifetime. The conclusion being that it's happening now, it's happening all the time, but you just can't see it happen. It's just something that's occurring. Theophrastus, his writings on minerals and their properties, ores and rocks, were studied through the Renaissance. In fact, you can still download or order those books very easily online and be able to read through them. But there's no way around it. The most important thing to a lot of the early thinkers was the age of the Earth. And the reason why it was important to a lot of people is because it tied very closely to their systems of belief, usually what we would call a religion or their philosophy of life. So the age and origins of Earth has been a matter of religious and scientific interest since ancient times. The Sumerians and Babylonians believed that the Earth was between 200 and 400,000 years old. The Egyptians had a much younger Earth. They put it about 15,000 to about 49,000 years old, depending on the source. The Greeks and the Romans had a wide range. Some of them thought the Earth was eternal. It had no beginning. Others put it very young, at about 2,400 years old. The Zoroastrians said it was about 12,000 years old. The Hindus, or in Hinduism, there are texts that suggest that the Earth is 4.3 billion years old, which is very interesting because that's not very far away from the scientifically accepted age today. The Chinese culture had a date of 3,900 or 39,000 years, and the Mayans actually put an exact date on this. They're not the only ones that ever put an exact date on it, but they said the Earth was formed in the year 3114 BC. So this is something that has been moving around amongst different cultures for a very long time. It's a key focus. How old is the Earth? If it's a religious question, of course, the question is when did God create the Earth? The age of the Earth was not just only important to those cultures I just listed on the previous section. The Christian faith actually had a very deep interest in this as well. And while several people had worked on it, the main person who is cited is Archbishop James Ussher. In 1650, he published his popular and influential treatise called The Annals of the Old Testament. In fact, here is the cover page for it. And it calculated that creation occurred at nightfall on October 22nd, 4004 BC. Okay, so you may have heard at some point in your life that a lot of people in the Western world believe the Earth is 6,000 years old. Well, if you go 4004 BC to the current year, which is, this is being filmed in 2025, so this would put it 6,029 years old, October 22nd in the evening. This is relatively consistent with other biblically based chronologies produced by Kepler and Newton. This was a commonly accepted belief. And if you're interested in this, you can get in here and you can order the book, of course, and you could read it. In the beginning, God created the heavens and the earth, Genesis 1:1, which beginning of time, according to our chronology, fell upon the entrance of the night preceding the 23rd day of October in the day of the Julian calendar, 710. Of course, which translates to 4004 BC. Okay? So that's an important thing to start with. This is geology, of course, is going to look at this question. Geologists are going to look at this question of how old is the Earth and does this make sense? So the original geologists actually came out of the religious faiths trying to confirm these questions. Now, the interest that people had in the Earth and its relationship to the Bible extended far beyond just the origins of the Earth, the age of the Earth. They also wanted to be able to interpret the creation of the Earth and be able to see its creation within the rocks itself. And so this gives rise to a philosophy called catastrophism. And I want to bring this up here. We got an interesting person I want to bring up in history. So in the early stages of the development of geology, efforts were made in Christian Western societies to reconcile biblical narratives of creation and the universal flood. So there's a creation event, and then there was a biblical worldwide universal flood that they call the deluge. These are not always treated as being the same event, and so there could be a large gap in time between the two of them. There was different philosophies on how this worked out, but a lot of them dug into the earth to be able to try to answer this question with new concepts about processes which had formed the earth. William Whiston is probably one of the most famous writers at this time. He published a book in 1696 where he argued that what God did to put human beings on Earth was he effectively terraformed a comet, and that a lot of the things that we see on the Earth are related to astronomical events that we see in the solar system, different bodies interacting with the Earth, and usually comets were the main things that they pointed at. And a lot of that is written in his theory. This book was extremely influential. The book is called A New Theory of the Earth, From Its Original to the Consummation of All Things, wherein the creation of the world in 6 days, the universal deluge, and the general conflagration, which means a giant fire or disaster, as laid down in the Holy Scriptures and shown to be perfectly agreeable to reason and philosophy. Effectively trying to say that the Bible and what we're seeing in the rocks and in the geological record, there is no controversy between these two. He's trying to show that there's a perfectly reasonable way to accomplish what exactly the Bible is describing. And one of the things that comes out of this, when you have a very young Earth with features that appear to be fairly old, it means that you have to have some way to get things done very quickly. And these things that you could do very quickly were usually and typically catastrophes. So one of the ideas we have to bring up is catastrophism. So catastrophism is the concept that the distant past consisted of epochs of paroxysmal and catastrophic action interposed between periods of comparative tranquility. So we have that all written right here. This simply means that there's a very rapid, sudden, and uncontrollable upheaval that will happen. Let's just say maybe a meteor hits the Earth, or there's some type of major flood event that comes in and carves all new landscapes. For those that were concerned about theology, and of course at the time that this was starting with catastrophism, this was pretty much everybody, such events could be supernatural in nature. The water did not have to come from the ocean, it didn't have to come from the rivers, it didn't even have to come from the sky. It could come from God or some other supernatural being. So the oft-cited example, especially in the West, was the deluge, also known as Noah's flood. So here we have an image of, somebody drew this, I found this online. This is a picture of the Earth, and coming across this is a large global flood that is covering everything. And of course, through that prism of Noah's flood, a lot of people were looking at the history of Earth and trying to explain and interpret it in that way. And a lot of them actually believe that the Earth was 6,000 years old up until fairly recently, as a consequence of the way that they were thinking in terms of their catastrophism. This, of course, gives rise to a concept called flood geology. Flood geology is one of the early, widely believed paradigms within catastrophism. The development of it occurred over a period of about 350 years before it suddenly kind of went cold. We'll get into where that goes. But flood geology development attributed Earth strata. These are the layers, the rock layers you're seeing all over the planet, and fossils to Noah's flood, shaping early geological thought by integrating biblical narratives with observations of marine fossils and sedimentary layers. So a lot of these people were going out into the Earth and studying the landscapes and studying the fossils, and they saw it as kind of a way of understanding and validating the architecture of Earth as coming from a supernatural entity, in particular, the entity of the Bible. Cultural and institutional support. Its popularity was bolstered by its alignment with Christian doctrine. It was taught in universities and supported by the clergy, making it a dominant paradigm in geological discourse until the mid-19th century. This gentleman here, whose name is in French, and I have difficulty saying it, but I believe it's Saussure, is credited with popularizing the term geology in 1779 through his work Travel in the Alps, building upon the earlier introduction of the term by his colleague Deluc in 1778. So the very first time we see the word geologist use, or geology used, is by this gentleman during his period of time working in the Alps and publishing that work. By the late 1700s, the development of catastrophism and its reconciliation with the Bible had given rise to a new, refined idea of catastrophism that we call Neptunism today. So the theory of Neptunism is simply this: the theory that rocks formed from a primordial ocean. In other words, that the entire Earth had been covered by an early ocean of liquid water, necessary for flood geology to provide a systematic, water-based explanation for rock formation aligning with biblical flood narratives. And the principle of this is that all rocks precipitated from aqueous solution. In other words, all rocks on Earth came from water. So this is something that is kind of interesting, the idea that we have granite located up here in this image. It's the most famous rock. Almost everybody who's ever been outside or has ever looked at a countertop always asks themselves, is that granite? Or they can identify granite pretty quickly. The second most famous rock is probably limestone. And so fossiliferous limestones are pretty common on planet Earth. We could look at these two things, and what the Neptunus argument is, these both came from oceans. They both precipitated from water. And the way that the Neptunus arrived at this was through a classification scheme. So Neptunus classified deposits by age and formation. And they would say that there was a primary rock, a primary source. These are the oldest fossiliferous rocks. In other words, there's no fossils in them. And crystalline rocks, like granite. So when we look at granite, we'll notice that granite has these interlocking crystals. There are different colors. We'll get into that in a different lecture. But here we see these different crystals all interlocking. However, when we look at the fossiliferous limestone, it clearly has fossils in it. The granite does not. And so the granite falls into the realm of being primary. That this would have been the old foundation stone of the earth, the cornerstone, God's cornerstone or foundation stone for the planet. This is an old, ancient rock, if you're a Neptunist. On top of that would be a secondary one that would be fossiliferous sedimentary rocks overlying the primary rocks, like shale, or in this case, perhaps a fossiliferous limestone. So it's not uncommon to find limestone around the earth and to look at it and realize this one is coming secondary. So this is a secondary rock. The tertiary ones are, tertiary, meaning third, younger sediments overlying the secondary rock. So you might have limestone, and then sitting on top of the limestone might be a sandstone. So sandstones in this case would be tertiary, as opposed to secondary, like the limestones that would be underneath it. And of course, the most recent, youngest stuff would be quaternary, which is the fourth group. Quaternary, the Q-U-A-T, meaning four. Recent, and this would be common for cobbles and sands and things like this. Things that are happening effectively right now. So let's give you an example of an outcrop as it would be seen by the Neptunus in terms of what would be, in this case, a tertiary and a quaternary deposit. So here we see an example of a quaternary deposit that is overlying a tertiary deposit as it would be interpreted by the Neptunus. So here we could see a clear difference between these two formations here, right? Here we have these cobbles that are laid on top. Of course, there's going to be a very young surface that's going to be formed over here, but effectively, this is some type of flood deposit. And in fact, modern geologists would argue this was probably put there with the assistance of water. So that is supported of the Neptunist argument. But there's going to be other problems coming forward to show that this is a more sophisticated image than we realize. Underneath here is the older unit. This older unit under here is tertiary. In other words, this is the next layer down. And in theory, you should go between or below the tertiary, you should find a secondary deposit, and then you go far enough, you will actually find granite or something crystalline without fossils in it. So this is how they would look at things, looking at them in four groups. Now, what's really interesting, if you're interested in geology as it's taught today, we still use the term quaternary and tertiary in our geologic timescale, but we use them in a different way than the way the Neptunus brought them in. But they're useful terms. Quaternary deposits, generally speaking, do look like this on land masses. Now, the Neptunus didn't operate without cracks in their theory being presented to them from time to time. This was a little troublesome for them. The first person to do so in a way that is substantially contributive to the way that we look at geology today is Anton Morrow, who in the 1740s was looking at rocks from the South Pacific, which was an area that was actively being explored at that time. He was looking at those rocks, and what he recognized is that basalt, which is a black rock, it's crystalline, it doesn't have fossils in it, was linked to volcanic activity. And he also linked it to mountain formation. Mountains possibly even forming today, not requiring a catastrophe, but through a natural process. This suggests that basalt formed from molten material. And in fact, we observe that today. This is the lava. This is lava that is cooling and it's forming this black rock right here. That black rock is crystalline basalt. This laying early groundwork against water-based Neptunism and establishing a new paradigm, Plutonism. Remember, under the Neptunist world, basalt is a primitive or primary rock that goes back to the very beginnings of the Earth. It's the one of the foundation stones, kind of like granite. This is very revolutionary in the Neptunist world to come in and say, no, this is not a rock that is formed from oceans, but in fact is formed by heat, and it's being erupted today. Mr. Morrow is also the first person to discriminate the existence of igneous rocks from sedimentary rocks. Nobody had ever done that previously in an official way in the field that we call geology today. So the first person to make that discrimination on a scientific level. Plutonism posits that some rocks, like basalt, form from the cooling and solidification of molten material within or on Earth's surface, driven by internal heat. And that is what an igneous rock is. It's a rock that is formed from those processes. Plutonism, it emphasizes ongoing geological processes such as volcanism and uplift, and continuously reshapes the Earth's crust, as opposed to water-based deposition, which is you have a catastrophe, there's a bunch of deposition that happens, and then the Earth goes quiet for an extended period of time. What Plutonism is saying is the change is always happening. This is a very, very different worldview. And this gives rise to the Neptunist-Plutonist controversy. This is a very big deal in the history of geology and the development of our worldview on how the Earth functions. This had a profound effect upon people like Darwin in the biological sciences later on. The Neptunists argue that granite and basalt precipitated from a primordial ocean. It's very old. But their crystalline textures and volcanic associations supported Plutonist views of igneous rocks. One of the things that Morrow was effectively saying was basalt is not, in fact, a primitive or primordial rock that goes back to the primordial ocean. But it's an example of a young rock that is part of a process that is ongoing today and has probably been going on for a while. And we're going to get into how controversial that is here in a moment, because a while, is it 6,000 years, or is it longer, or is it shorter? It's an interesting question, and it turned into a pretty big knife fight in the geosciences right around the late 1700s and certainly by the early 1800s. At this point, we need to introduce a very important character, historical figure in the development of geology, James Hutton. James Hutton was a Scottish geologist. He was a part of the Scottish Enlightenment. He was a Plutonist. He was very aware of the findings of Mr. Morrow, and he was a friend of the famous philosopher David Hume. He was also friends with James Watt. Yes, that James Watt, the one that the Watt is named after. That's his buddy. And Adam Smith. Adam Smith, of course, is the person who wrote The Wealth of Nations, and a lot of people would say is one of the fathers of what they call capitalism in economics. So he's surrounded by people that are thinking very deeply. Often called the father of modern geology. So he's a big deal in the Scottish Enlightenment and certainly has a profound effect upon the world today. He revolutionized earth sciences with his observations and theories on geological processes, emphasizing the Earth's dynamic and cyclical nature based on empirical evidence. Empirical evidence in the sense that you can derive it by measuring it, seeing it, feeling it, experiencing it. The word experiment has that same sense in it, right? To gain experience. And so through empirical evidence, you can compile this information over time. Now, Hutton proposed something very new. Hutton proposed that the Earth was immensely old. As he would describe it in his writings, with no vestige of a beginning, no prospect of an end. It's a very famous line from his writings. No vestige of beginning means, as far as he's concerned, there's no start. The Earth just always was. And it has no prospect of going away. It'll just be around forever. Based on his observations of slow geological processes like erosion and uplift, he was able to make the argument that almost anything could happen given enough time. In fact, we'll get into the processes of his thinking here in a moment. Challenged the then accepted biblical timeline of a few thousand years. In his world, the Earth was immensely old, far older than the Bible interpretation that was being proffered at that time allowed for. This is not going to make him very popular. And But he does wind up having some very important contributions to pushing us from the Neptunus view to the current views that we have today. So he's that springboard. So whereas the Neptunists were using catastrophes and water events, even Noah's flood, to explain many of the phenomena they saw on planet Earth's surface, James Hutton was using a different approach. He was taking a Plutonist approach where he was saying heat and time. And in doing so, he developed a new paradigm for geology that we call uniformitarianism, to be able to make it all work. So uniformitarianism is the geological principle introduced by James Hutton that asserts the following things, and these are very important. And these are very simplistic, and Hutton, of course, explains it in much broader terms, or in greater terms and with much greater detail. But effectively, they boil down to these principles: that the Earth's ancient features are shaped by the same natural processes, that's erosion, sedimentation, volcanism, observed today. So if something was happening 60 million years ago, say the creation of a volcano, well, that volcano would have been forming the same way that volcanoes form today. So that you would just simply take what you're seeing today and extrapolate that out to the past. Operating consistently over vast timescales, as encapsulated in its quote, "The present is the key to the past." So if you want to know what was happening then, look at current analogs of what's going on today. A classic example of this will be shown right here between his farm, Slyhouse's farm in Scotland, and this outcrop in Scotland right here. Not this one specifically, but one very similar to it. That current processes are a guide supporting the idea of a dynamic ancient Earth shaped gradually rather than by catastrophic events. Gradually. Okay, a lot of people refer to this as gradualism. What he noticed, for example, at Slyhouse's, this is his farm, located here, is on this farm there's a series of ditches, and what he realized is that when it rained, during torrential rain events, a large amount of that topsoil would wash into the gullies, and those gullies would then feed that sediment down into the rivers, and the rivers would eventually discharge out into the ocean. And he recognized that what we're looking at when we look at marine shales and bedded or layered rocks that are of marine origin, he recognized that a lot of this was deposited by rivers out into those oceans. And so, as his friend John Playfair would write about James Hutton, Hutton noticed a vast proportion of the present rocks are composed of materials afforded by the destruction of bodies, animal, vegetable, and mineral of more ancient formation. In other words, this is not being deposited by a large ocean straight out of the water, precipitated straight out, but in fact was composed of broken bits of matter from a former existence up on the land. And that would take a large amount of time to be able to create these things. And here we have a shale that originally formed in the water, but is derived from the land, is now back onto the land. So it's gone through a very complicated cycle. This principle, of course, is hostile to Neptunism, as it emphasizes ongoing, observable geological processes like erosion and volcanism over a singular catastrophic water-based origin. Okay? So Hutton did a lot of studies on these sediments coming off of his farm washing out, and it occurred to him, if you go on too long without some type of cycle that is going to refurnish the soils from time to time, eventually all the soil will be washed off and be all washed off into the ocean. But that hasn't happened. So somehow the rocks, the landscapes are being rejuvenated. And that was something that was a huge revolution in geology at that time. Another massive controversy during his period of time was this question of granite and basalt, right? We talked about what happened with Mr. Morrow, the fact that he had made this argument, but that was dealt with some hostility. I mean, the Neptunists didn't like this. It was part of the Neptunus-Plutonist controversy. And in 1785, at Glen Tilted, Scotland, James Hutton decided he was going to go out and observe this and see if he could make a determination as to whether or not granite, which was, again, God's foundation stone, it was this primary rock, should have been the ancient heartstone of the earth itself. The question is is this heart, this cornerstone of the earth, is this an example of an ancient rock or a young one? And so what he knew of was a location based upon information that he had, that there was a place where granite and another type of rock called a schist was nearby to one another. And he decided to march on out there and have a look at it to find out whether or not this was a primitive crystalline rock that formed and rained out of a primitive ocean, or whether or not it was born molten. And what he discovered is that you get to the point where the granites get into close contact with the schist, and you can actually find out where they match, and that's called a contact. And we're looking here at this image right here. This is actually from Glen Tilt. This is the very place that he went to. And at Glen Tilt, what he notices is that this pink material, which is the granite, and the gray material, which is the schist, you'll notice what's happening here. There's these veins of granite injecting itself into the schist. Well, this is very, very important. One, if it's injecting itself, it's liquid. And two, if it's injecting itself, it's younger. What he demonstrated here is that this granite in this situation is not an example of an ancient stone that dates back to the origins of the earth itself, but an example of a younger rock that was born molten, that came into this area through some process caused by heat from somewhere within the earth, again supporting the Plutonist view, and injecting itself into the rocks around it. Okay, so providing evidence for his Plutonist theory that granite was a young rock formed from molten material injected into the Earth's crust, not old water-formed rocks. So this was in 1785 in Glen Tilt where he did this. And by the way, there's a lot of tourists that stop by there and they visit this outcrop. It's a very famous place to go and visit if you are into geotourism and you happen to be in Scotland. Another important thing that he had to introduce was proof that the Earth was immensely old, right? So just simply showing that there is a heat source that could have done this is one thing, but again, he needs to demonstrate that there's time. And one of the places where he was able to do this is a place called Sicker Point. This happened in 1788, 3 years after his discovery over at Glen Tilt. He visited Sicker Point in Scotland, where he observed a striking unconformity. So we'll get into unconformities at a different lecture, but this is where rock layers, which should be flat, laying on top of each other, are instead not lying flat on top of each other. They're at an angle with one another. In this case, it's called an angular unconformity. So that image is right here. So we can see rocks that are located right here. They are almost straight up and down. And sitting on top of it is another series of rocks, and these are tilted also, but they're not conformable. They're not sitting on top of the rocks properly. So we also know that the rock layers always form flat when they originally formed. That was something that was even known at this time. A guy named Nicholas Steno had already figured all this information out. He was aware of that these rock layers would have been formed flat. So he's looking at this. He says if these rock layers were originally formed flat and these are on top of it, the only way that you can do this is that you must have some type of cycle of deposition. At some point, the earth heaved and rotated those rocks up. Erosion had to bevel off the top parts of those rocks. So whatever was here that was extending up into the air is now gone. So it's eroded off. And that a new series of deposition had to happen across the top of it. And that deposition is now rotated into the orientation that we're seeing right here. This is a stunning unconformity. And what was pretty obvious is that this is not something that can happen in 6,000 years. This is a dynamic, very complicated geologic history, but a dynamic history of constant change, constant movement at the Earth's surface. And we're seeing that at Sicker Point. Again, another place that geologists that do geotourism go visit. It's kind of a place where a lot of homage is done to the history of geology, this location at Sicker Point. So this supported his theory of a dynamic ancient Earth. And in a lot of ways, this was kind of the very first nail in the coffin for the Neptunist worldview. The Plutonists started to get something started. Now, James Hutton is only going to live until about 1797, the final death knell for the Neptunists won't actually occur until the 1830s. Which leads us to the next very important name in geology, Charles Lyell. If James Hutton was the father of geology, Charles Lyell was its biggest proponent and probably one of the most important thinkers that ever came along in geology in terms of a philosophy and pushing it out and making it the discipline that it is today. He was a Plutonist. He was a follower of Hutton, but he didn't actually study and work during the time of Hutton. Hutton died in 1797. Charles Lyell was born in 1797. They didn't know each other. He was a Scottish geologist whose work established him as the founder of modern geology, particularly through his development of uniformitarianism. He is the one that took Hutton's ideas and started to really put them out into the public. That in Hutton's own time, most of his ideas were not accepted, certainly not by most of the geologists of that time. But this would change. A lot of Hutton had a small following. That following did tell young geologists about those ideas as a kind of a secondary or alternative theory to what was going on with the Neptunists. Charles Lyell was aware of this. In fact, he learned of it largely through Playfair's book, which was published in 1802. Remember, Playfair is the gentleman I quoted over here, and you can still buy his book. Lyell read that book. He read several books, was very familiar with the ideas of uniformitarianism, and was sold. So, again, Hutton didn't live to see his ideas accepted, but Lyell sold it later on. His seminal work, Principles of Geology, argued against catastrophism, and in fact, it's regarded as the first modern geology textbook. Everybody read it, including Charles Darwin, who was a very good friend of Charles Lyell. The combination of evidence and eloquence in Principles convinced a wide range of readers of the significance of this concept called deep time for understanding the Earth and the environment. This strongly influenced Darwin's theory of evolution because suddenly, if the Earth was quite old, then the animals that lived on the Earth were also quite old, and therefore evolution became a more viable theory. His writing accomplished what Hutton could not, which was to get it worldwide attention. Right? He changed everything. Okay, this idea of deep time would play a major role with people like Lord Kelvin to find out exactly how old the Earth was. A lot of people didn't like the idea of no vestige of beginning. You know, the Earth probably has a beginning. In fact, that is one of the great contributions of of Lord Kelvin. Is that he did show that the Earth, in fact, does have a beginning. But Lyell was one of the guys that said, hey, if you got enough time, extraordinary things can start to happen. So you only need incremental change under uniformitarianism to get immense things like mountain ranges to change and to rise and ocean basins to drop and things like this. Now, of course, there have been refinements to uniformitarianism since it was originally proposed by Hutton and later on really pushed by Lyell in his concepts of deep time. And the most modern refinement of that uniformitarianism idea, which is still uniformitarianist, but has a slight turn to it, a slight change to it, is actualism. And it assumes the following: that natural laws, that being the laws of physics and chemistry, have remained constant through time. So hydrogen has always acted like hydrogen, helium has acted like helium, oxygen like oxygen. The laws of universal gravitation are functioning in much the same way as they have always functioned. But it focuses on applying these laws to interpret past events without assuming the rate or intensity of processes was always the same. So, for example, in the early Earth, we believe that there were these large bombardments of asteroids and comets, and of course that would play a major effect or a major role in shaping the surface of the Earth and the composition of the Earth as that is occurring. Now, people would say, well, each one of those is catastrophes. But remember, the key point of a uniformitarian viewpoint is that if it's constantly happening, it's a constant process. It's no longer catastrophism. It's uniformitarianism. It's a process where this is occurring, right, over a long enough period of time. Is it still happening to today? Of course. We have little meteorites hitting the Earth all the time, every single day. They're called meteor showers, right? Every once in a while we have a large explosion that happens in the atmosphere, and sometimes we have a Tunguska-style event where we actually see things that are damaged on the ground. So these things have always been happening. The question is it with the same rate or intensity as it always has? No, it's obviously changed. Variations in environmental conditions or event magnitudes that might not be common today is another important thing to think about. Have we always had glaciers all over the earth? No. There have been periods of time where there were very few glaciers. There's also periods of time where there were large glaciers. In fact, some people even have the idea of an ice ball Earth. So those environmental conditions or magnitudes can sway greatly. But that doesn't make it catastrophist. It just means that the application of the laws or under the conditions that existed at that time produced that result. Repeated episodic or catastrophic events become uniformitarian over long time frames, right? So if a volcano erupts and the entire volcano not only erupts lava, which is very standard, could happen gradually, but every once in a while certain volcanoes will blow themselves completely away and then start to rebuild. Is the blowing away of that volcano in that event like a Mount Tahama, which is a volcano that is believed to have existed in Northern California, the explosion of that large volcano, is that a catastrophist event? No, because it's something that volcanoes do. It's just part of the process. So it doesn't become catastrophist to recognize that this occurs. If it's a repeated, reproducible process that has been happening throughout Earth history and is compliant with the natural laws, it is still uniformitarian, but it's uniformitarian under the actualism viewpoint. A great example of actualism in play are the Lake Missoula megaflood. So Lake Missoula was this giant area that is now currently basically open land. Here's an image of where this was. This is a big valley here that was completely covered with water at one point. And the water at one point drained very quickly. Some people would even say catastrophically drained out. If it's going to be catastrophic, it implies certain things. Remember, we were talking about catastrophism and how that works. But under actualism, what it says is that the draining of water probably through these valleys is pretty standard. What we're seeing is a very large magnitude flood that is moving through here. In fact, this is a huge magnitude flood. But these types of floods may have been more common and as a direct consequence of the movement of ice sheets and things like this that are happening at that time. And so people that study the Lake Missoula megaflood, they immediately lock in on these large ripples right here. So here are these ripples. This is water moving across these ripples here that create these. Again, the same physics that creates ripples in little creeks and on the beach are also the same physics that are creating these ripples, except these ripples are giant. That's a building right there on top of that ripple. There's another building on top of that ripple and back over here. Just to give you an idea. So to get ripples that large, you need a large amount of water moving at a very high rate. Okay. But the events that create the conditions for which this mega flood would have occurred are completely standard uniformitarian ways that this would happen. This is not God's wrath or something like this. We can in fact find mega flood deposits in different places on Earth, and in every single case we can explain them through a standard natural process, which is completely translatable to uniformitarianism. So since the Plutonists were no longer going to be following the guidebook of the Neptunists, which was really to look at historical texts, to look at religious texts, to be able to figure out how they wanted to interpret their geology or to use it as a guidebook, they actually needed to use a different approach. And so naturally they fell into the scientific method. The scientific method has some key concepts that you need to know. We're going to jump into this. We'll expound upon this as the lecture series fills out over time. But the first one that I want to bring up is the word hypothesis. A hypothesis is a testable prediction about geological phenomena. For example, the idea, hey, this local volcano created this ash layer that we're looking at. So volcanic ash formed this layer. That could be a testable hypothesis. You can go through a series of tests to figure that out. Another important term is inductive reasoning. This is generalizing from observations. So an example of this would be inferring ground movement from fault patterns. Another form of inductive reasoning is to do a series of experiments and extrapolating that to say, we've learned from these experiments that this seems to be what happens in our experiments, and we're going to extrapolate that out to all conditions. That could be a problem, and we'll get into what that problem is in a little bit. Deductive reasoning is predicting specific outcomes from general theories. So younger layers, for example, are deposited on older layers. And that's almost always the case. There's some bizarre situations that occur when things are injected into one another and stuff, but for the most part, as long as gravity is playing a role and deposition is happening, sedimentary layers will form layer cake with the youngest one on top, and the oldest one will be stacked at the bottom. Pretty straightforward. Empirical evidence is observable, measurable data. This would be like rock composition, seismic data, taking a ruler and figuring out the distance between two things, and that's a number that you can write down into a journal. That's a great way to do it. Conclusions, evidence-based findings, validating or refining hypothesis. So a conclusion, we'll get into what a conclusion is and what makes something a conclusion, because sometimes what we think is a conclusion really needs to be fed right back into the process again. And we also need to introduce the concept of the induction fallacy. So the induction fallacy is overgeneralizing from limited data. So assuming all rocks are volcanic from just a few samples. So this was something that was happening with the Neptunus view, was they were doing the induction fallacy. They were looking at a very few number of examples relative to what is available on the surface of the planet. They were largely unaware of igneous processes happening in South America. They were aware of volcanoes and stuff. This is something they understood existed. But in terms of it being a foundation stone creating new young rocks, that was something they didn't encounter a whole lot. So the induction fallacy is overgeneralization from limited data and limited examples. A type of observation that you can make in here is, for example, we have a little bit of ice. This is a rock that is right here, and you'll notice this rock has these steep grooves moved into it. That's right next to the glacier. And so one can very rapidly have the hypothesis that this glacial polish, which is what we call it, this polished rock with these grooves on it, is created by the movement of glaciers across the surface of that rock, where it's ripping those lines and those grooves and polishing off that rock. That can be tested. And how do you test it? Well, you go to other locations and you see if, hey, where glaciers exist, is there rock polish there? And are those grooves there? And if so, we could start to build that story. We could start to build that case over time. If you look at one location, it might not work out so well. You got to look at many locations to really get a feel for what is really going on. I always think it's important to take the time to recognize some of the major contributors. This is not a comprehensive list by any stretch of the imagination. There's actually names on here that I wish I could put on, but again, this would turn into a class about the scientific method as opposed to being about geology. But you gotta make sure that you put down the main contributors so that you got a starting point in case you want to go and start looking at issues or questions about what we're doing. So Aristotle, again, this is another important name in history, emphasized observation and classification of natural phenomenon. Very big deal. Really the inventor of logic as we know it today. We have another gentleman whose name I cannot pronounce, but he was Latinized as Alhazen. So Alhazen lived right around 1000 AD. Pioneered experimentation and empirical evidence. He's a really big deal, in fact, and this is a picture of Alhazen right here, and this is Galileo on the same on the front piece of this book to just show you how important these two thinkers were to people putting together the scientific method, even as early as 1647 when that thing was published. Francis Bacon formalized systematic observation and induction. In other words, the initial scientific method to make sure you go through a process, and by going through the process, you're hitting a checklist to make sure that everything you're doing works, and that what you're doing is deriving knowledge and information and facts and data and using it to build that argument that you're putting together. Again, I don't want to get ahead of myself, but Francis Bacon was the first one who formalized that. Galileo Galilei used experiments to test his theories. So this idea of using, in his case, he was using all kinds of different little contraptions. He was dropping balls off of the Leaning Tower of Pisa, things like this. Those experiments were providing the experience that he needed to be able to show the theoretical. And that theoretical was a big deal, later on applied by Sir Isaac Newton. René Descartes stressed deductive reasoning and skepticism. And in fact, the scientific method has that built in through that repeatability process. The idea you probably have heard before is that if something is repeatable and you keep getting the same result, then it no longer is just a generalization from a basic observation, but in fact, it's a generalization from a whole lot of data. And so the chances of it being true go up as you have those iterations, those experiments, and you get into deductive reasoning. John Locke promoted empirical knowledge from sensory experience. In other words, he was the guy that really came in and said, if you could measure it, you could see it, you could feel it, you could touch it, and you can quantify it, it's a very big value in what you're trying to do. It also meant that if things that are metaphysical are now excluded, and that's kind of something that is a big deal. Metaphysical meaning things in the spirit realm, things that you can't see, things that you can't touch, things that you can't feel explicitly. I mean, you might be able to feel it in your heart or in your mind or something like this. But, the actions of an angel, unless the angel manifests itself and picks up a rock and moves it or something like this, that's not empirical knowledge, right? So the sensory experience, which is, say, your five senses, if it can pick it up, that's where you're going to derive your knowledge from. David Hume highlighted causality and skepticism in scientific inquiry. In fact, he was the big guy, the thinker, the big mind that came in and introduced the concerns about the induction fallacy, which is no matter how many times you study something, there's always a slight chance you're wrong. And that you can never have perfect knowledge of a thing because there's always that one time it's going to be off. And that one time that it's off is going to require some type of correction to what you currently believe. So David Hume is one of those guys that emphasized that very strongly. And of course, David Hume is the mentor to James Hutton, just to show you that lineage. And that lineage is then coming from Hutton to Lyell and then eventually to you, the viewer. So let's go ahead and do a kind of walkthrough of a potential question that might be asked in the scientific method and some of the procedures you might go through to make sure that you're, checking all the boxes to make sure that what you're doing is actually acquiring the knowledge, not just simply going through the motions or trying to get some type of biased response where you think that you already know what's going on, so you make that result come out of your results. And so the scientific method is designed to kind of get you, to keep you on the straight and narrow, to make sure that you get an honest result from this. So what does this look like? So observation. In this case that we're going to be working with is noticing concentrated seismic activity in central California. So seismic activity, which means earthquakes for the most part, right? Shaking, ground movement, things like this. The types of questions we could be asking, we can ask some very specific questions like, why do major earthquakes occur near the San Andreas Fault, which is running through central California? That's a really good question. By the way, that's one of the central questions that was asked by geologists for 100 years in California. Why was it happening along that fault system? Why is it still happening along that fault system? And how well do we understand it? We can do preparatory research. The preparatory research, which means going back into the archives and seeing what other people have already learned, what they've already discovered, what other work and what other data they have, and start working from that. Because you could repeat what other people have done, but one of the things that you could do is not only repeat and replicate the data that they have, but you could also simultaneously go and supplement it and not add your own data to it. So that preparatory research includes reviewing geological surveys, maps, and prior studies. For example, here we see a geological map of San Benito, California. In this region here, this is the city of San Juan Bautista. The San Andreas Fault moves right here, moving right here. See if I can get the cursor on it. And we'll notice that the rocks are very different on each side. Here they're colored in a brown color. They're not that color in nature, but that's the color they are on the map, and largely because the color code corresponds to their age, right? So the rocks up here that are in the yellow and the light creams and light yellows are all much younger than the red ones down here and the blue ones down here. So these are older rocks, and these are relatively younger rocks compared to these. So we have the question, why is this happening? We have all this earthquake data that's going on. We got all the seismic data that's going on. The San Andreas Fault clearly has rocks on different sides of it, which is unusual because, as we know, rock layers spread out and should be continuous on both sides, but they're not. So something's going on with the San Andreas Fault. So we can ask this question. We can do this preparatory research, and we can see that there's clearly something going on. We can propose a testable hypothesis or propose a testable explanation, which is a hypothesis. So, for example, active tectonic plates form the San Andreas Fault, right? We can go out and we could check that. We can go out and do experiments to go and validate this. So some of these experiments could be conducting field studies, doing lab analysis, or simulations, right? The simulations in a lab, or we can go out and take measurements using GPS, right? So data collection, measuring rock properties, seismic data, or mineral composition. Here we're actually doing just a straight, old-fashioned observation of the fault right here. This is after the great 1906 San Francisco earthquake that killed over 3,000 people and destroyed 80% of the city of San Francisco. This was a devastating event for Central and Northern California. But here we clearly see what the fault does. It ruptures across here. We can come out and we could take photos. We can measure these things. And if it was to ever move again, we could go out, we could measure that data again, not only on the seismograph to see what the earthquake looks like, but also to see how the land itself actually shifted. And we can then look at broader questions of, is this in fact a plate tectonic boundary that the San Andreas Fault is believed to be? So those are the kinds of hypotheses that we can do. And that's what the scientific method looks like. That's what geological field work looks like, and what experimentation looks like. And putting it all together and validating it through a repetition of this. So collecting a large amount of data will seem to buttress and improve the result. And so that is something we should work for. And now that we've gone out, we've mapped the fault, we've done our preparatory research, we're putting it all together, we're going to go and analyze all that data and compare it to what we found previously in our preparatory research, and we're going to begin to do an interpretation. So we'll analyze that data, we'll interpret the results to confirm or refute the hypothesis, and then we'll draw a conclusion. Now, we're going to be drawing evidence-based findings for reports or publications. And what's really important is that we understand that other people have to be able to come in, review this, have it be understandable, have it be interpretable by them. It can't just be something that you just put out into a journal and everybody says, oh, it's great. Somebody needs to be able to go out and say, yeah, I can see where they took that measurement, and that measurement is the same measurement I would get if I was to measure it myself. Iteration. Iteration is refining a hypothesis or asking new questions based upon the results. Why do we want to do this? Because we want to minimize the risk of the induction fallacy. If we don't do that iteration in the process, and we allow the things to be not only reproducible, but also to be reproducible at other locations, in other words, to gain greater knowledge, then that induction fallacy starts to loom pretty large if we have just a scant amount of information. If we only have the San Francisco earthquake of 1906 as our data point, it's almost impossible to reason out that San Andreas Fault is likely the plate boundary between the Pacific Ocean and what is going on in North America, on the North American continent. We'll get into that later on. Okay, but you can't do that just based upon a single earthquake. But if you're mapping it, you're doing earthquake data, and you're looking at things over a very wide range, and you're collecting thousands and thousands and thousands of observations over an extended period of time, then all of a sudden it becomes pretty clear that the San Andreas does seem to be functioning in this capacity. And in fact, it's very difficult to argue that it is not arguing in that capacity. So let's sum this all up. right? First, you raise a question about the natural world, whatever it is that you're interested in. This is a scientific method in general. You do some background research, which is to say collect scientific data that relate to the question. You construct a hypothesis that may answer the question or may not. You develop observations and or experiments that test the hypothesis. So you want to basically attack your beliefs. You want to attack your question, okay, by collecting as much data as possible. You analyze that data, and if the reports support the hypothesis, you share that with the scientific community. If the results partially support or do not support the hypothesis, you still share that with the community, but guess what? You also try again. You push it in. Sometimes finding out that something isn't the answer is just as valuable as finding out that it is the answer. Okay? So that's the whole process of the scientific method, is you're constantly pushing it through and you're refining it, minimizing risks, and maximizing what is the likelihood that you have a real answer. So now that we've gone through the scientific method and how geologists try to apply it to problems, and we'll probably dig into this a little bit deeper as we go through the lecture series. But we also have to begin with the concept of a rock. What is a rock, right? This all starts with James Hutton and his colleagues looking at rocks and asking themselves, where did that come from? And from their understanding of the origin of rocks, they have worked out whether or not it's heat and time versus catastrophism and an ocean, a primordial ocean that did things, right? The Plutonism versus Neptunism. And under Plutonism, it's very clear that what rocks are simply naturally occurring agglomerations of crystals that we call minerals. And the minerals that compose a rock strongly influence its nature and appearance. It gives a lot of its properties is what are the constituent minerals that are in there. Is it made out of calcium carbonate? Is it quartz? Is it feldspar? A rock's texture, such as its size, shape, or arrangement of its constituent minerals, also has an effect on its appearance. And when we look over here, we can notice that there are all kinds of different rocks here with different colors, different textures. Some of them even have fossil material in here, which is what this last bullet point says. Some rocks may even have fossil material in them. Others may contain or produce fluids like petroleum. And so when we're looking over here, that's a fossil, that circular object right in there. There's fossil material in here, fossils in here. But here's one where we don't see any fossils. It's just the grains are just tiny. They're just really small. All of these rocks were formed in different ways, in different environments, and probably at different times. And yet we find them here in this pile of rubble and material that is located in Alaska. So a very important series of geological processes have brought them all together at this location where you can get a very nice photograph of their different colors and their different textures. But what are they? They're agglomerations of minerals. And the origins of these minerals are quite important. In fact, one of the principles that was brought in by Hutton is that, remember, old things become new things. In other words, they're always cycling. So he created the concept called a rock cycle. And here we're seeing material, in this case, this is living material, fossil material, that is now deposited into a new rock, along with other things that are not fossiliferous, such as these other materials over here. So, pretty cool. One of the consequences of Hutton's ideas is the creation of a rock cycle, that the material that used to exist can become other things in time, and in fact that rocks are constantly cycling around. Igneous rocks, as we discussed earlier, were discovered by Mr. Morrow. But sedimentary rocks, which are these types of these layered rocks that we're seeing right here, are derived from the weathering of pre-existing rocks. The sediments will undergo what we call lithification, which means conversion into rocks. So you're taking a bunch of silt, sand, clay, and you compress it, you cement it, and it'll form a nice layer. That layer becomes a sandstone, a siltstone, a shale, whatever it winds up being. It accumulates in layers at the Earth's surface. Those are your sedimentary rocks. And so here we're seeing nice, beautiful sedimentary rocks that are deposited. And then there's a third type of rock that was determined theoretically to have existed by Hutton and was later on confirmed, which is the metamorphic rocks. So metamorphic rocks are formed by changing pre-existing igneous, sedimentary, or other metamorphic rocks. And so if you take a rock, it doesn't matter if it's an igneous rock like this basalt up here, or you take a stack of sedimentary rocks, whether it's sandstone, shale, or whatever, and you put it into a large amount of pressure and a large amount of heat, it'll recrystallize. And those recrystallizations will create new textures and new rock minerals. And you get things like metamorphic rocks, where we see these layers are banded with black layers and white layers swirling through it. I mean, it almost looks like some type of candy that has been stretched out and then squished back together again and left in the earth. It's extraordinary. And what they realize is that there's these three different types. And it turns out that over time, they can change into the other types. Just depends upon the amount of time. This is what gives birth to the rock cycle. So the rock cycle is a process that allows us to visualize the interrelationships among the different parts of the Earth system, right? So it turns out that material coming out of volcanoes probably was at another place on Earth at some point in the past. It served some other purpose. It was the minerals, the atoms that were in the minerals were allocated differently. And so the Earth is constantly shifting and changing things over time. And so the rock cycle allows us to understand the origins of igneous, sedimentary, and metamorphic rocks, which is not always easy to do, by the way, and see that each type is linked to the others by Earth processes. In other words, you don't require some type of catastrophe to happen. You don't require a primordial ocean. The rock cycle is constantly kicking out all the different kinds of rocks on Earth, constantly and at the same time, depending on where you are. In some places, the creation of sand is being generated on beaches. In the past, where those beaches are, it might not have been that. It might have been limestone. Or it could have been part of a mountain belt where there was volcanoes, or there were metamorphic rocks being squished into existence as large land masses are pressing their weight and their heat into that area. So the rock cycle was first conceptualized by James Hutton, who first theorized the origins of metamorphic rocks based upon experiments. And this is a diagram where you have imagine we could start right here, a volcanic rock, let's say this lava. This lava it cools down, it crystallizes, and it forms a extrusive igneous rock, something like a basalt. That basalt can then be eroded and broken up and turned into a sediment like sandstone. That sandstone can then be pressed together and cemented together over time to create a sedimentary layer like what we see in the Grand Canyon. The Grand Canyon can then at some point be buried and large amounts of heat applied to it so that those layers in the Grand Canyon wind up becoming metamorphic materials like marbles and quartzites. And eventually, if you add sufficient heat to a specific location, that rock will begin to melt, and then you restart the cycle. What's really interesting is that everywhere in the cycle is connected to all the other places in the cycle. Sand can get cycled into metamorphic rocks and become quartzites. Metamorphic rocks can get cycled back into sedimentary rocks without going through the igneous process. So the Earth is constantly cycling and manufacturing different types of rocks all at the same time. It does not require catastrophes to get it done. And that is the key innovation of James Hutton. So now that we've introduced rocks and the rock cycle, which is really to understand the constituent parts of the Earth itself, right? When you pick up a rock, you're holding the Earth itself. We also need to understand the context of the Earth. What is the cosmic address of the Earth? What are its neighbors like? What is the product from which the Earth formed? And so we need to talk about that a little bit, and that will give us a good springboard for the rest of the class. Earth is the third planet in the solar system from the Sun. So there are a series of planets that extend from the Sun being the central star of our solar system. Earth orbits at an average distance of about 93 million miles, or 150 million kilometers from the Sun, and is one of 8 planets in our solar system. Now, the solar system includes the Sun, 8 other planets, moons, and I mean lots and lots of moons, especially around Jupiter and Saturn, asteroids by the thousands, and comets. And when you look at the solar system, in fact, there's a really nice little graphic, you can see it rotating around. It shows all the little objects that have been mapped in the solar system, and the sun, of course, is located in the middle. The planets in our solar system orbit the sun in nearly the same plane, known as the ecliptic plane. So there's the sun, and going around it is the Earth. But in that same plane is Mercury, is Venus, is Jupiter, Saturn, Venus, Uranus, Neptune. They're all in that same plane. Okay? There's not like the Earth is going this way and Jupiter's coming and going in a different direction. They're all going around like a racetrack around the sun. The planets also orbit in the same direction, so it's not like Saturn is going in a different direction. They're all going the same direction around the sun. And the implication is that all of these planets and everything in the solar system kind of, for the most part, started at about the same time. So it implies all formed at the same time in the same event. Now things can get moved and bumped and changed over time, but the original process seems to be original to the solar system. Whatever created the solar system is creating everything in that solar system. So the solar system is also part of a larger community. The Earth's solar system resides in the Milky Way galaxy. So the galaxy is a barred spiral galaxy, approximately 100,000 light years in diameter. Light year. That's the distance it takes for light to go in 1 year. So the Milky Way galaxy, and there's a nice image of it right here. This is an artistic rendering of it. Here's the bar in the middle, so that's what we mean by it being a barred spiral galaxy, and here's the spiral arms coming off. Here's our solar system located right about here. This is the galactic center right here, and we are on a local arm called the Orion arm, which is right here. And you'll notice that we're about 2/3 of the way out. So we're not right in the center, but we are definitely within this galaxy, okay? The overall galaxy contains an estimated 100 to 400 billion stars. That's a large number of stars. And most of them have planets, by the way, around them. So it's fascinating. And there's also the building of new stars and the destruction of old ones. It's happening all the time. So what's happening in the rest of the galaxy is also believed to have been happening in our own solar system. So as we said earlier, the solar system is within the Orion arm, a minor spiral arm, and is located about 27,000 light years from the galaxy's central supermassive black hole named Sagittarius A star. So Sagittarius A star is a black hole that is located right here in the center, and when we say it's supermassive, it's millions of times larger than our sun. And pretty much everything in the solar system is in orbit around it, including our sun. So our sun is orbiting the supermassive black hole, and then the Earth is the third planet orbiting around the sun, which is orbiting the supermassive black hole. Okay? Our solar system orbits the galactic center about every 225 to 250 million years. So that means the last time the Earth was at this position around the galactic center, the last time it had a galactic year, dinosaurs were alive. So that kind of thing just blows my mind when you think about the amount of time that went by. So we're going around this thing. There were dinosaurs here the last time we were at this position in the galaxy. The galactic plane and the ecliptic plane are inclined at about 60 degrees to each other. So while the solar system is all going in a racetrack around the sun is actually at an angle in terms of its solar system to the ecliptic plane, to the galactic plane. So the sun is actually looks like what we're seeing in this image right here in the lower right. It's moving to the right here, but you can see the planets are actually moving almost like corkscrewing around the sun as it makes its trip around Sagittarius A star. And the great thing about being in the Milky Way galaxy is you can see it. If you go to a dark place at night on a cloudless night, when you don't actually have a bright moon, so if it's really dark, you can look up and sure enough, you can see the beautiful Milky Way galaxy, which is depicted right here in this image. Okay. And there's some things that you can pick out if you look. I want to point out the location of Scorpio. This is a constellation. There's several important stars in here, Antares, Lambda Scorpii, which is the great thing about this one here is this Lambda is a triple star system. So this is 3 stars orbiting around each other. This one here is a quintuple star system. This is 5 that are all gravitationally locked in with one another. So there's no rule that says that the only thing that can orbit a star is planets. You can actually have stars orbit other stars. Antares is a binary star system. So this is a beautiful, giant, absolutely massive star. And it has another star going around it. And in fact, it's also very close to where there's a little nursery for the creation of brand new stars. And we'll be showing that here in a moment. Next thing I want to show you is the location of Sagittarius A star. So here's the galactic center. So here we see the Milky Way. Right there is the center of the Milky Way galaxy. And if you happen to know where Scorpio is, you can come out, you follow the tail of Scorpio, and you follow it right up that band, and there's Sagittarius A star, the center of the Milky Way galaxy. It's right in the middle of that dust cloud. And in fact, this is a image of it. We actually have a photograph of Sagittarius A star, and what you'll notice is the central event horizon. The event horizon meaning that's the point at which light can no longer return. So it's absorbing light, it's bringing it in, and then it has the disk around there that is refracting light and directing it towards us from the stars around it. It's absolutely incredible what's happening out over here. Sagittarius A star is a supermassive black hole around which you are currently orbiting. Located right near Antares is this cloud right here. It's a cloud complex. It's the closest star-producing region to Earth. And located right at this position right here, you'll notice those little pink spots over there. Those are brand new stars forming within the last several thousand years. These are things that are, they've been going on for thousands and thousands of years, but these are stars that are forming, and they're forming from the dust in space. So here we have this cloud complex, or something we would call a nebula, and this nebula is producing these stars. And so we believe that this is the location from which our own sun, not specifically this one, but these conditions are what produce our own sun in the solar system, a nebula, or a cloud of gas and dust. So now the question is, how do you go from gas clouds and dust, nebula, to stars, planets, and ultimately to us? And that's something called the nebular theory. The solar nebula, which is what we believe that the sun formed from, out of a very similar situation to what I just showed you. The solar nebula was a massive gas and dust cloud that consisted of hydrogen, helium, and microscopic dust grains. And just like what we're seeing out there forming stars right now. And what we believe happens is the nebula will collapse under its own gravitation. In other words, all of these objects are floating around in space. They're interacting with each other, and they begin to pull towards one another. And in so much as things start to grow towards one another or to pull towards one another, the gravitational field increases, and it pulls more and more material into it. So that collapse tends to cause things to begin to, if it's a big dust ball, will actually start to rotate. And it'll actually start to form a disk, almost like taking a ball of pizza dough and throwing it up into the air. It spins out, but at the same time, it gets squatter, moves out this direction, and so it becomes smaller tighter, it's a faster spinning disk. Through collisions and other interactions, the gases and particles begin to orbit in one plane. So just like that pizza, right, being thrown up into the air, with most of the matter condensing into the center where the proto-sun, and later what will become the sun, forms. So all of the gases start to go towards the middle, where the main mass is going to be. But not everything makes its way out there. The stuff on the outside, for example, forms planetesimals. Planetesimals are little tiny orbiting, I wouldn't say little tiny, they're large, but they're early protoplanets, right? This is rocky material that is moving around and accumulating dust and gas as it's going around that solar disk, that nebula, and cleaning up all of this stuff. You might be asking yourself, well, do we have any evidence that this is the case? It turns out we do. We can actually look at some of these young stars. In fact, here's one out of that exact same cloud complex right here. This is AS209. The central star is right here, and around there is a disk of material, and you'll notice that there's these gaps, these rings here. It is believed that in between these rings and this ring, here and here and here and here and all these other ones, is a planet that is forming as we're, as we're taking this image, that it's sweeping up and vacuuming up all of that material and adding to itself all of that mass and clearing out that nebula. And so here we've got the central star that is forming. Here's the nebula that is condensing and forming planets and planetesimals. And the planetesimals and inner planets like Mercury, Venus, Earth, and Mars will begin to form by accreting metallic and rocky substances. So the heavier, rocky stuff is accumulating closer to the sun. Larger outer planets like Jupiter and Saturn begin forming by accreting fragments of ices like water, carbon dioxide, methane, and other ices. Hydrogen gas is another one. And one of the things that we observe is that when we look to see if other stars have planets orbiting around them, the remnants of this old disk, it turns out not only do we have it at our solar system, but here's another one. This is an exoplanet. So these are planets that are orbiting around stars that are not our sun, HR 8799. This has been observed over a period of 7 years, and those little white dots that you're seeing there going around, this is in the lower right-hand image, those are planets that are orbiting that star. So we know that stars and planets, they kind of go together. And so when you create a spinning disk and you get a star in the center, it's very likely that you're also going to produce planets that are going to be going around them as well. In fact, we're now discovering that almost all of the star systems that we're observing have planets around them. So all of this material is going to be crashing in from an astronomical source, right? Meteorites, comets, dust, gas, accreting very rapidly. And of course, as it starts to happen, it starts to accelerate and it starts to sweep up almost everything around it. As that material accretes to the Earth early on, the temperature would have been high enough for iron and nickel to melt. When you take things and you crash them together, you produce a large amount of heat, a lot of friction and things like this, to the point where all the metals are going to start to melt together. And we have argued that this is going to lead to the formation of a layered structure for Earth. We call this differentiation. So what happens? Well, the metals will sink to the center, which is the core. The Earth's magnetic field, once that occurs, so you get a bunch of metals down there, especially if they're liquid metals, the Earth's magnetic field will start to develop. So suddenly you'll get a magnetic field developed around the Earth. Molten silicate materials rose to produce a primitive crust. So all of your silica, your oxygen, potassium, sodium, a lot of that stuff will go out to the outside because it's not as dense as the liquids in those metals. And over time, you can establish the three basic divisions of the Earth's interior, what we call the core, the mantle, and the crust. And if we were to slice the Earth open, we have a pretty good understanding of what's going on down there. Again, we'll get to a lecture that deals with Earth's interior and how we know this. But we actually have a pretty good understanding that the Earth's inner outermost portion is almost all metal, iron and nickel. It's actually solid at the very center with an ocean of molten metal around it. And then there's a rocky mantle above it. Then above that rocky mantle is the crust, and that's what we reside upon. From this differentiation, what would have separated out from it, the atmosphere would have pushed itself out to the outer portion, just like steam boiling out of a boiling pot of water. And that the ocean would have evolved from the volcanic gases. In fact, when we study volcanoes that are still venting this portion of the earth, the mantle in particular, we discover that there's a large amount of water vapor still coming out. So there's still a lot of water down in the earth. And we believe that the earth fully formed by about 4.54 billion years ago. So the earth is quite old, and it certainly has a beginning. How did we acquire that date? Again, we'll come to that in a later lecture. Now, there's a lot of controversy about what was going on in that early Earth, and we care deeply about what happened in that early Earth for reasons we're going to get to in a moment. There are two competing hypotheses on early Earth and what it was like: the hot Earth hypothesis and the cold Earth hypothesis. So the hot Earth hypothesis was the main theory that was around when I was a young student, that the early Earth was intensely hot from these cometary and from the accretion, all this material, the comets and the asteroids and everything coming in and hitting the Earth, these meteor impacts slamming into the surface of the Earth, heating everything up. There was a large amount of radioactive decay that would have happened in certain short half-life elements. So molten magma oceans driven by formation heat, radioactive decay, and frequent meteorite impacts. They call this the late heavy bombardment as part of this. Delaying liquid water and life until cooling occurred till about 4.4 billion years ago. So what the early Earth, for a lot of people looking at this for a very long time, was that there was nothing to stand on. The entire surface was a magma ocean. That's been called into question lately. There's growing evidence that certainly there were pockets at a minimum of cool Earth. The cold Earth hypothesis is that the Earth cooled rapidly after formation. So the Earth formed, there might have been a magma ocean, but it was very short-lived. That a solid crust had formed very rapidly, and that liquid water oceans existed by 4.4 billion years ago. And therefore life-friendly conditions despite a faint young sun. So the sun was just starting to really get going in its process of what it's doing right now. And the reason why this is a big deal is because this would have been the conditions by which life would have formed on Earth, or potentially could have formed by Earth right around that time. So some people have argued that life came later. Some would argue that it came right in the early conditions. And so this is something that people have looked a lot at. When we look at the world's oldest minerals, it turns out the world's oldest minerals, like this 4.4 billion year old zircon, this is a mineral that formed under ordinary cold Earth conditions. That there was an ocean that was available. The isotopes are, we'll get into isotopes again later on. The isotopes are consistent with a nice cool Earth. Nothing extraordinary. Hot Earth likely dominated immediately post-formation. Evidence like ancient zircons leans towards a cold Earth by 4.4 billion years ago. So the GA stands for gigaannum, which means billion years ago, indicating a transition from hot to cooler conditions, which enabled early habitability. In other words, life. So Earth is very unique in that not only does it have the right conditions for life, but for water, but it probably had it extremely early on. And in fact, we do find evidence of life in some of the oldest rocks on Earth. So from all of this, through all of this heat, from these cometary bombardments, from these meteor impacts, what does the Earth look like? So we've got to talk about the face of Earth as we have encountered it as humans today. What we've discovered is that there's two major zones that we need to be aware of, which is one, the continents, which is the land masses where we live. And then there's the ocean basins. And it turns out there's land, or there's earth or rock and material at the bottom of the ocean basin, but the ocean basins are covered by water. So we have a large amount of water. We have an atmosphere. We've got these continents. The continents represent about 29% of the Earth's surface. The ocean is about 71%. And at the northern and southernmost extents of the Earth, we have continents that are covered with ice sheet. Up here, this is a continent covered with ice sheet. And so ice is an important factor on the face of the Earth. The other thing that we've learned about the Earth and its evolution is that portions of it are incredibly old, and portions of it are incredibly young, and portions of it are so young that it's forming today. When we look at the hearts of the continents, for example, this Canadian shield that we see here, or the African shield, or the Brazilian shield, these are very old rocks. In fact, we got 4 billion-year-old rocks right here in Canada. But over here on the west coast of the United States and Canada, we have some of the youngest mountain belts on planet Earth. They're rising today. Why do we have 4 billion-year-old stuff here and current growth today? Same thing happening with the Appalachian Mountains. We have mountain chains that formed. In this case, between 200 and 400 million years ago? 480 million years ago? And then we come over, but those mountains are no longer growing. They're eroding and they're falling apart. Yet when you go to the Himalaya, they're uplifting today. The mountains of the west coast of the United States and the west coast of all of South America are rising today. So the Earth is in constant motion. Mountains are rising up, old mountains are eroding. Catastrophism doesn't explain any of this. This requires some new theory. So the Earth is really unique in that it has a geosphere, and that geosphere has a rock cycle. It has a hydrosphere, and that hydrosphere has a water cycle going on it. So Earth has the right pressure and the right temperature conditions for water to be in all three phases, liquid, solid, and gas, which is what gives rise to the weather conditions, the reason why it rains on your head and why it snows during certain parts of the year. It has an atmosphere with lots of oxygen in it that we can breathe. And those three things together are believed to give rise to the early conditions for the creation of a biosphere on Earth. The science behind this is just fascinating. But the Earth is just so unique in so many ways. But the question is it unique because we don't have a whole lot of experience with it? In other words, the induction fallacy. Is it possible that there are other Earth-like planets out there with these same conditions? Statistically, yes. But the question is whether or not they have life is a totally different question. Now, why do we study the Earth? Why do we study geology at all? Well, people in the Earth, of course, have a very close connection. It's where we're from. We're from here. But also we have to live here. So we have to understand how the natural hazards on Earth work and how they impact us, how they can impact our communities. Geologists study volcanoes. We study floods, tsunamis, earthquakes, and landslides. And these are natural processes but become hazards when they occur where people live. So here we've got a natural landslide, right? This is not catastrophism. This mountain is constantly shedding debris down onto this area, which is now a roadside. Same thing with this flooding condition. This was probably always a floodplain, and for whatever reason, we've decided to occupy it. This is, again, not catastrophism. This is uniformitarianism playing a role. This is probably, both of these are probably predictable outcomes. The question is, when is it going to happen, not if it's going to happen. Now, if you're going to be a geologist, you have to accept the fact that you're going to be doing field work. And it's not really a bad thing to do. It's a lot of fun. Here's a geologist out there sampling lava in Hawaii. You can see how hot it is. Another thing that we do is a lot of laboratory experiments. We look at different kinds of sand. In this case, you could be doing studies on sand, where it comes from, looking at ancient sandstones, looking at the way that water moves through it, looking at the chemical compositions. all kinds of different things that are important to us. And of course, sometimes you're just going out and you're looking at formations like this and asking yourself, what did this? What is the story of the Earth? What is it trying to tell us? And lastly, people are deeply interested in the resources that we're getting from the Earth, right? The Earth gives us life. It sustains us. It gives us the building materials we need for our homes, for our clothing, and also for other animals that we're dependent upon. So what are the resources the Earth gives us? Well, this includes the water, the soil. It gives us the metallic and non-metallic minerals. It gives us all of the energy. So all of this is produced from very complicated chemical reactions within the Earth, or in this case with plants. These carrots are growing through a complicated interaction between the soils and the sun and the atmosphere and the hydrosphere interacting all in a complicated way. These are gold nuggets. Most gold nuggets are actually originated from volcanic processes. And of course, energy, this is coal that is burning over here. Energy is derived from a sedimentary process whereby living organisms, and usually it's in the form of forests, are buried, and that coal is preserved and pressed, with the water's pressed out of a coal bed, and the remaining carbon can be burned as an energy source. So if the Earth isn't fitting the Neptunist view, and instead there's a large amount of heat down there, how does the heat manifest the changes that we see on Earth over time? Is it a series of pistons moving up and down? Are things sliding around? What is going on? How do things actually operate? And so now the Plutonists have to take the mantle and actually answer those questions for themselves. How does the Earth change with heat and time, as opposed to an ocean and catastrophes? And that'll be in our next lecture. Again, this is Paul Day. Thank you for taking the time to listen to this lecture and being a part of this class. I hope to have you in all the other future lessons. Take care.